Welcome to this training session on lithium-ion battery manufacturing. In this course, we will walk through the complete journey of how lithium-ion batteries are made, from the very beginning of raw material preparation, all the way to the final assembly and quality testing. Our goal is to help you understand each step of the process, so you can connect your daily work in the factory to the bigger picture of battery production. Let's begin our journey from the front to the end of Li-ion battery manufacturing. In this training, our goal is to provide you with a comprehensive understanding of lithium-ion battery manufacturing. You'll learn how today's battery plants are set up, and you'll see how each major step connects together. The process is divided into four main stages: electrode manufacturing, assembly, formation and finishing, and finally, module production. By the end, you'll understand how all these stages fit into the bigger production flow. Here is the roadmap for this training. We'll start with a quick overview of how battery cells are manufactured. Then, we'll move through each major step: electrode manufacturing, cell assembly, and cell formation with finishing. Next, we'll cover how cells are packed into larger units. Finally, we'll look at some process overview diagrams that tie everything together. Think of this as your guide to the journey we're about to take through the battery factory. 2030 Forecasted Battery Cell Manufacturing Map. This map shows the forecast for battery cell manufacturing capacity across the US and Canada by the year 2030. Each circle represents the size of a planned or operating factory, and the company logos indicate which manufacturers are leading the build-out. Names such as LG, SK Innovation, Panasonic, Samsung, Tesla, Ford, GM's Ultium Cells, and many more. By 2030, total production capacity is expected to reach over 1 terawatt-hour. Most of this, about 97%, is planned for passenger cars, light trucks, and SUVs. Only a small portion, around 3%, is dedicated to commercial vehicles, such as buses and heavy-duty trucks. The important point is this: the US and Canada are rapidly scaling up local battery production. For workers in these plants, this means more opportunities, faster growth, and a stronger focus on quality and safety to meet the demand from the EV market. This diagram illustrates the complete process of manufacturing a lithium-ion battery cell. The process starts with electrode manufacturing, where powders are mixed, coated, dried, pressed, and cut into the right shapes. Next, in cell assembly, these electrodes are stacked or wound, packaged, welded, and filled with electrolyte. Finally, in the cell finishing stage, the cells go through formation, aging, and storage before being ready for use. We'll go into each step in detail later, but for now, just remember this: the process moves in three main stages: making the electrodes, assembling the cell, and finishing the cell. Each step builds on the previous one to create a safe, high-quality battery. Now, let's look at the costs behind battery manufacturing. On the left chart, you see how material costs are divided. The cathode material is by far the most expensive. It makes up nearly half of the total cost. After that come the anode, separator, electrolyte, and other smaller parts. On the right chart, we see machinery and process costs. The biggest cost driver is formation, the process where we first charge and cycle the cells to make them stable. Next is the dry room, which is essential because it controls moisture during many steps, from coating to final sealing. After that, winding, coating, and mixing also take a significant share. The key message here is this: the cathode material and the formation process are the biggest cost factors in battery manufacturing. Understanding this helps explain why precision, safety, and efficiency in these steps are so important in the factory. This slide illustrates how machinery costs are distributed across the various stages of the battery-making process. At the front end, coating machines are the largest investment. Approximately 80% of the cost is allocated to this step, as precision coating is crucial for electrode quality. In the middle stage, winding or stacking machines account for approximately 70% of the cost. That's because the accuracy of how electrodes are stacked or wound directly affects the performance and safety of the cell. At the back end, the largest expense is cell formation and aging, accounting for approximately 70%. This stage requires specialized equipment and time to properly form and stabilize the battery. To put it simply, electrode fabrication drives front-end costs, cell assembly drives middle-end costs, and packing and formation drive back-end costs. Each stage has its own major investment, highlighting why efficiency and quality are crucial at every point. One way the battery industry is reducing costs and improving efficiency is through the use of new, integrated machinery. Instead of using separate equipment for coating, drying, and calendaring, these processes can now be combined into a single, continuous system, as shown here. This kind of innovation increases productivity, measured in parts per minute, and it also improves accuracy and yield. For workers, this means fewer handling steps, tighter and cleaner electrodes, and fewer problems, such as burrs on the edges. In short, smarter machines enable us to produce higher quality batteries at lower costs. What you see here is an early type of automated stacking machine that uses a method called Z-folding. The machine alternates cathode and anode sheets, with a separator layer in between, folding them back and forth like the letter Z. This process ensures that the electrodes and separators are stacked evenly and tightly, which is critical for both performance and safety of the cell. Automation enables this process to work faster and more consistently compared to manual stacking. The first generation of folding machines represented a significant step forward in battery production, laying the groundwork for today's more advanced stacking and winding systems. Here we see the second generation of stacking equipment. Unlike the earlier Z-folding machines, this system simultaneously feeds the anode, separator, and cathode rolls. These three layers move together in a zigzag path, while the machine cuts and stacks them automatically into cell units. By integrating stacking and cutting into one machine, the process becomes faster and more precise. It reduces handling steps, improves layer alignment, and increases production yield. This generation of equipment represents a significant improvement in automation, enabling us to build cells with higher accuracy, reduced waste, and improved efficiency. So far, we've focused on materials and machines, but there are other major factors that impact the cost of battery production. First, scale matters. When factories expand production, they benefit from economies of scale. Larger production volumes can cut cell costs by over 30%. Second, labor costs play a huge role. In Poland, labor costs approximately $6 per kilowatt hour, while in Germany, it exceeds $25. That's a big difference, and it's one reason why automation is being pushed in every plant worldwide. Third, location also drives cost. In China, producing a cell may cost around $106 per kilowatt hour, while in Norway, it can be more than $150. Finally, energy cost is another key factor. For example, producing electricity in Sweden costs only about $1.40 per kilowatt hour, but in Germany, it's nearly $7. The key takeaway is that scale, labor, location, and energy all significantly impact the competitiveness of a factory. That's why efficiency and automation in our daily work are so important. This slide provides an overview of the global battery supply chain. On the left, you see the 2021 ranking of countries. China leads in almost every category, followed by the US, Germany, and a few others. This ranking reflects strength in raw materials, manufacturing capacity, regulations, and demand. On the right, we see how major car makers like VW, Daimler, Hyundai, Ford, and GM are partnering with leading battery makers such as CATL, LG, SK Innovation, and Northvolt. These partnerships are critical because automakers cannot secure enough batteries without strong ties to manufacturers. The key message is, battery production is now a global race, and strong supply chain links between automakers and cell manufacturers are what drive the industry forward. This diagram illustrates the complete midstream process of manufacturing a lithium-ion battery. On the left, you can see how anode and cathode materials are prepared. Powders are mixed with binders and solvents to form a slurry, which is then applied onto copper or aluminum foil. Separators are added between the two electrodes to maintain their separation. The electrolyte, produced in separate batch reactors, is later injected into the cell to allow ions to move during charging and discharging. A large plant needs dozens of mixers and reactors, over 130 just for a 10 gigawatt-hour facility. Each step must be carefully controlled to ensure that quality factors, such as pH, viscosity, and conductivity, are maintained. This overview illustrates how the various components, anode, cathode, separator, and electrolyte, come together to form the battery cell. We'll go into each of these steps in more detail in the next sections. This diagram from LG Energy Solution illustrates the complete process of manufacturing a lithium-ion battery. The production can be grouped into three main stages. First is electrode manufacturing, also known as the front-end process. This step, which includes mixing, coating, pressing, and cutting, accounts for about 40% of the total cost. Second is cell assembly, the middle-end process. Here, the electrodes are stacked or wound together with separators, packaged, welded, and filled with electrolyte. This stage accounts for approximately 30% of the total cost. Third is cell formation and module assembly, the back-end process. At this stage, the cells are charged and discharged for the first time, aged to achieve stability, inspected, and then arranged into modules and packs. This also accounts for about 30% of the total cost. Across these stages, the four core components, graphite anode, metal oxide cathode, separator, and electrolyte, are carefully packed into a casing, with terminals exposed for use. Once the cells are complete, they are connected to form modules, and these modules are then built into packs. This slide gives us the big picture. Next, we'll zoom into each stage step by step to see how the details come together on the factory floor. This concludes the overview section for battery cell manufacturing. Thank you.